Hi all, my name is Juha. I'm calling in from Helsinki, Finland, where it is a Finnish summer day, 12 degrees and raining. And I'll set up the screen share here. What I will be talking about today is, this is going to be a sort of lightweight talk on a couple of topics that have been, let's say, rather relevant recently in the work that I've done in data modeling and so on. But the idea here is to talk about the kind of gap between the kind of perhaps idealistic view of the conceptual data model, the reality of what exists in the business, and then the kind of more practical analytical use case of a star schema or a dimensional model. So practical approach, kind of philosophy, a thinking process or way of thinking rather than a theoretical approach to anything. We will be basically going through the topics very soon. Let me just start with some basics. There are many familiar faces and names here, but if we haven't met, I'm Juha Korpela, as I said, from Eli Technologies. Eli is, of course, the data modeling tool company. I'll show you a few screenshots during this presentation, even though I have to say at this point, this is not going to be a product demonstration as such. I'm more about talking about the actual modeling content than the tool itself. But in any case, my role at Eli is to be responsible of the product itself, where we are going with that, what we do with that. I also do a lot of this kind of methodological stuff and training and speaking gigs like this. 11, 12 years in data management, doing all sorts of stuff. You can hit me up on LinkedIn. Absolutely like to connect with everyone. What we will be talking about today, as I said, a practical look at this whole thing, kind of a light snack to start your second day at Knowledge Gap. Something that, as I consider that many of the people here are, of course, experienced modelers, so something that might not be new to anyone. I would say something that we all kind of instinctively do when we do dimensional modeling especially, but possibly and hopefully what I'm going to be presenting here gives you some kind of ideas and insights that might help you kind of organize your thoughts when you're doing this work. So basically focusing on kind of practical rules of thumb that I have personally seen to work really well in real life situations that are not really based on any sophisticated, highly mathematical theory. I leave that to Christian. When we discussed this topic, I remember, Christian, you sent me a link to your article on pretty much the same topic where you had very, very precisely defined how this actually works in a mathematical sense. I hardly understood anything about that, so I'm not good in maths. So I thought that the approach that I take here is slightly different. The philosophy of how we move this kind of normalized view of the traditional conceptual data modeling, what exists in the world, what are the things, what are the objects and people and places and events and so on, how we move from that to something that is closer to the implementation, the dimensional model as basically a way of presenting the data in a form that is easy to utilize in certain situations. So this kind of a practical approach to this, which I think, at least for me, is a very often encountered situation in real life organizations. So no theory, no maths, purely kind of personal experiences and thoughts on what seems to be working quite well and how this thought process works. A couple of notes on terminology. I will be talking about dimensional models and star schemas here. By those, I mean a model which has a fact in the center and then multiple dimensions, or any number of dimensions around it. I will most likely be more or less imprecise with my terminology during this show, but don't worry about that. And by a conceptual data model, I also kind of mean the usual way of doing modeling. So more or less normalized model where all the entities are basically things that exist in real world, and then you have the relationships and so on. So kind of a higher level understanding, and then we have the more focused idea of what we want to do with that data. So this is the approach. Here we are. This is where we start. And the background, basically the reasoning why I wanted to talk about this and thought that it might be useful is that everyone does this dimensional modeling. Everyone uses star schemas. In every organization, you have your data marts, you have your Power BI data sets, whatnot. You have this because it works in these specific situations really quite well. And I know, Francesco, you are already, I think, like grinding your teeth, but I have name dropped you here at the bottom that there are problems, of course, with this star schema approach, and Francesco's updated approach to it solves many of those. So I'm not going to go into that. That's your topic, Francesco. But I think the thing here is that the star schema has been around for ages. We know there are guides and literature and whatnot how to create this model. You know what sort of rules pertain to it. There are not too many guides and literature to bridge the gap between this kind of higher level normalized model and the more detailed, very focused star schema. And as especially us from the data warehousing background know very well, there are kind of these competing schools of thought that do not like to interact very much. So we tend to see that they are kind of separate groups of models that don't have much overlap and they don't have much to do with each other. For this reason, I often encounter situations where, for example, I'm auditing or reviewing a solution somewhere where the developers or the designers or the modelers who are working with a project are basically they realize that they have this self-service BI situation. So they design a star schema directly, jump into it, figure out your fact, here's the dimensions, map it to your data warehouse or your data sources even directly or whatever, and there you go. But my point here is that, in fact, approaching even the dimensional model use cases through the conceptual modeling kind of ideology is very, very powerful way of doing this thing right. So the problems that I see happening quite a lot with this, and I'd like to spend a little bit time here because these are kind of real life examples from all kinds of projects. Often we also see that the star schema of the dimensional model, it attempts to solve all the possible problems the organization has. We try to cram into it all kinds of solutions, all kinds of answers, all kinds of viewpoints into data. So we try to figure out any possible data that has to do with the topic that we're handling. We try to fit it into a single model. So one model answers every question. The problem here is that we haven't really properly defined the actual requirements of the kind of analysis, the problems that we have there. And the, let's say, natural reaction of data engineers and developers usually is that they just try to somehow fit everything into it. They know we need to have facts, they know we need to have dimensions, there's something there already, and then you get a new requirement or someone from the business says, you know, that this doesn't actually exactly do what I wanted, and then they try to cram into more stuff into the same model. So we get models that are confusing. They are developed in a haphazard fashion, built from small pieces here and there. There are inaccuracies in the data. They are extremely difficult to maintain after this has been going on for a while, even though the model by its very structure is kind of super simple in the sense you have the facts and you have the dimensions and there you go. But trying to build them like this leads to impossible to maintain situations. Another core thing is, and I've recently seen this happen, is that even though, you know, all of this discussion about these data models and the very good rules and everything, you can get the Kimball books and whatnot, the very basics are often quite wrong in the everyday implementations. The fact grain is one of the most obvious things that I tend to see, where the fact table has been chosen often in such a way that it is something that you get from the data sources as it is, and then you just try to fit in all the dimensions around whatever source data you have. This tends to happen, and the actual level of detail the business needs is not necessarily even considered here. And when they then come back to you, they say to the development team that, hey, I can't get the invoices out of this. Then they add more facts around it, and they maintain still the old one because still it manages to answer some of those questions. And obviously the keys, everyone knows who has done data modeling that you have to figure out your keys. You have the primary keys, you have the foreign keys, but still we're seeing data models, dimensional models especially, I think for some reason, where the primary keys are not chosen correctly for the intended level of detail. And that's then causing like duplicates or unnecessary aggregation or something like that, where you would think that this basic level of thinking here would be already corrected, but it's not. Another thing with the facts, this is the problem with the dimensions. I've recently seen quite violently misused dimensions. As the kind of BI teams and the data engineers work on these, they encounter weird business logic. And because they are still kind of trying to fit everything into the single dimensional model, because that's the requirement, give us a single data model so that we can create our reports, they start forcing these dimensions to be kind of monsters, Frankenstein monsters, basically, of all kinds of things. Recently, I have, for example, seen product categories as part of the country dimension because in specific countries or groups of countries, only specific product categories were used, and that was kind of specific to a certain area of the world. So they were just cramming the product categories into the same dimension as rows. And stuff like this. And the end result here is that the user experience is pretty bad. The initial use cases perhaps might succeed because all of this weird stuff that people do is due to those requirements. It's an attempt to solve it, and eventually you get some of that right, and the initial use cases can be completed. But the idea of how to get forward from that is very difficult to grasp. These are prone to errors. You build a new solution, you don't remember that you have to filter the fact table with a specific field, otherwise you will get, duplicates or something. The interpretation of the data is unclear. You don't know what a single row means. And this leads to the fact that the numbers themselves are not trusted to be right. So it's a data quality thing that appears as a result of poor modeling practices. And again, all of these practices could be, of course, corrected by simply just following the rules. But for some reason, people are not very good at following these rules. So if we consider this as the reality of data modeling in the kind of trenches now, where people are building these star schemas, and then we perhaps, I don't know, maybe you guys have better experiences. This is just the kind of worst case scenarios that I've seen. If we compare this to the kind of perhaps more idealistic data modeling that, for example, we at Ellie often talk about, being the kind of modeling of the reality as it exists, the conceptual data models, we can kind of see that there are two different sorts of approaches here. One being the high-level understanding of, I want to map the world. I want to understand what exists in the world. And the other being basically the very use case driven approach, where you think that, okay, my analysts, they need these invoices to be analyzed by country and vendor and whatnot. So let's start building the stuff like that. And these two approaches coexist even in the same organization, in the same projects, but they don't often link very well together. So with these conceptual data models, kind of a normalized way of looking at the world, you figure out the real life business entities, you make it technology independent. Of course, even there we can see very often that there are mistakes being made. System specific entities kind of blend into the conceptual data model. these theoretically at least should be kind of infinitely reusable. If you model your invoicing data on the conceptual level, that should basically be it. No matter what the project is, what the use case is, the model should stay. And of course, the point here is that this kind of a model is a very powerful communication tool, because you can get the business people involved. And this is what we see at Ellie. We have a simple enough tool to make this understandable, and we get the business experts to participate in the modeling, to collaborate over the model, and thus helping the communication between the business and the IT. But there are problems here. If you go to this high level, you stay there, it's not always very easy to understand how to apply this. You're lacking details, and the model is kind of expanding to different sorts of directions. It's not always easy to focus on specific things. So of course, especially in those development teams with your data engineers, the preference is that you get a model that is focused on the specific problem that you have. So the star schema is basically, you implement it. Power BI is super happy with that, or Tableau or whatever. This is kind of a super easy blueprint for the developers to utilize. This is exactly what the sort of tables should look like, and this is how they link. And now you just, map it to your sources, and here we go. Sharp focus on something. I want to analyze this thing in terms of these other things. But if we stay on this level and never go to the higher level, we lose the big picture. We don't understand what the actual business reality looks like. We are not building something that is very reusable, because the choice of facts and dimensions is specific to a certain use case. And occasionally, due to the problems mentioned previously, these facts and dimensions can also become sort of artificial. They are not very easy in all cases to basically map into the kind of real life entities that the business handles in the everyday business processes. So they might end up being somewhat difficult to understand. Whereas if you just remain on the level of real life business entities and the relationships between them, that is something that anyone can read, basically. The facts and dimensions might be already quite difficult. So the point here is, why not both? Let's start with the higher level understanding of what exists in the world and figure out how to kind of practically easily derive the star schema, make those decisions on the level of this conceptual model. So that's the kind of magic trick today, how to design the logical level model, basically the more detailed level model of the star schema, while looking at the conceptual model and doing nothing else. And the idea here is that this kind of way of thinking basically is what I want to show today. So I personally prefer to design my star schemas by looking at a normalized conceptual model. And I do think this is kind of useful in many cases. So that's the intro, a general note on examples, and I will speed this up a little bit. We won't be going over time. I know Christian is very good with the clock. All the diagrams you're going to see screenshots from Ellie, cloud native business friendly data modeling tool. We have in Ellie two modeling layers. They are called conceptual and logical modeling layers, and the idea here is pretty much the same. We want the conceptual modeling layer to be business friendly, something that models the real world as it is, and the logical modeling layer is more detailed, aimed towards implementation design, basically. So this works quite well with our example of the kind of real world models and the use case specific star schema models here. And these layers can be linked entity to entity together in Ellie. And we will be using this. This is very useful in our examples to see what logical entity, what dimension, fact, etc., matches with which conceptual entity. Now, if you want to try this yourself, there is a 30-day free trial on our website, ellie.ai. No strings attached, except, of course, a salesperson might call you, but nevertheless, much recommended. So on to the actual example then, the conceptual model. And here this is an example of a conceptual model like we usually talk about them when we are talking about ELI and modeling with ELI. So it's a pretty standard ER model. We have the entities, we have the relationships. The relationships have this cardinality with the crow's feet here. The color codes of these entities are what we call entity types, which is an ELI specific thing. Here you see that the black boxes are called master data entities, and the blue ones are transactions, and the pink ones are what we call contracts, which is kind of a specific type, which has to do with the fact that the entity kind of exists for a period of time. But we don't actually have to focus on that. By the way, in the next ELI version, within a few weeks, this will become completely customizable, so you can use whatever entity types and colors you like. The point here is that the model is, as we discussed in the beginning, about real life things and their real life relations. So technology independent, even use case independent, scoped for a particular area in business language. And what we have here is we have purchase orders and invoices. And we know that this purchase order was assigned to this cost center in that business unit, and it was ordered from a vendor whose home country is something, and the purchase amount is allocated to specific accounts in some way, and then it's been invoiced in a series of invoices which are paid with payment transactions from a to a vendor bank account, of course owned by a vendor, which is in a bank country. We could imagine, for example, that the use case here would have to do with anti-money laundering. So we would like to know which cost centers are making purchases from vendors in which countries and where the money is actually going to. So payments are made to all kinds of banks in different countries, and we would perhaps like to see, if we're weirdly paying a lot of money to Cayman Islands while the vendors are actually all located in Europe. That would be somewhat weird. So very standard conceptual model, normalized view, relatively normalized view of how things are. Some prerequisites of making the conceptual model in such a way is that it has to have these actual real life things. We don't want to prematurely denormalize or optimize anything. Just, model it as it is. We have the links between the entities as they exist in some system somewhere. It's technology independent, but we know that the links exist, and they are somehow identifiable things there with some kinds of keys that identify the entities there. And this should be enough. It's correct enough for our dimensional design to succeed based on that model. Of course, we would like that the entities themselves are well defined. In ELI, this is built in such a way that all the entities and those conceptual models are entries in the business glossary, and these entities are being reused across models. So you can see that the bank is defined in such a way, and purchase orders are defined like this, and the collection of all these different entities with their definitions forms the glossary. And this is, of course, important for us to be able to understand what we are talking about here. But I'm not going to go more deeply into this glossary thingy now. What we want to start with now is the actual transformation of this model. So if we start with the fact, we need to answer the question, what do we want to analyze? And the trick number one basically here is that we have to find the fact from the conceptual model. So there must be a single entity in the conceptual model that will form the basis of our fact in the upcoming star schema model. The choice determines the grain of the fact. So what is the level of data we have? What does one row of the fact table mean? If we point at an entity and we say this is the fact, then one row in the fact table means that. It's of course possible that we are missing an entity from the model. We could have a many-to-many relationship, as we see here, where the allocation could be kind of added as a separate entity there, and that would actually be the fact. So it's possible that we don't see it immediately, but at that point, if we realize that this is actually the fact we're interested in, then we should add that as an entity. But I'm not going into that. The candidates we'll consider now are basically the entities circled here. And what we have to do, and this is now the first step in the thought process, point a finger at this, say, this is the fact. And that determines basically everything. So this is the single most important decision that you can actually make. For different business questions to be solved, we might need different facts, and that might need different models because we can't always have everything in single model. But this decision can also be pretty painful. You have to choose something. So we'll consider these two actually now. We'll focus this on these examples here, and the purchase invoice and the payment. And the grain is determined by the choice we make. So what does one row in the fact mean? It either means a purchase invoice if we choose that, or it is a payment. If we choose the purchase invoice entity as the fact entity, it means that the grain in the fact is at the level of individual invoices. So we can't go deeper than that. We only have invoice level data. So we have attributes like invoiced amount, invoice date, due date for the invoice, etc., etc. If we choose the payment entity, that's the grain. So we have that data now on the level of individual payments. So the attributes would be amount paid, transaction date, etc. So when we are building a single star schema, we have to choose a single fact table, right? But both of these kind of feel interesting. So how do we possibly reach a situation where we don't have to build separate models for every single possible thing, but we can kind of smartly combine at least some data from our interesting facts? So we're getting now to the kind of actual tricks here, and again, there's nothing weird here, there's nothing new here, just a way of thinking about this. And the first kind of trick, the thought that you have to kind of think about, if you want to combine these facts, you have to do some sort of an aggregation if you want to go kind of up in this direction. So if we want to be able to analyze both of these things here, we can aggregate the payments up to the purchase invoice. And I like to think about this as kind of physically like squishing those entities together. So we're saying that, okay, you know, this goes inside that. And this is aggregation is of course possible because there's a one-to-many relationship in this way. So we could, if we do that, we could calculate into our purchase invoice level fact something like paid amount so far, or count of payment transactions for this invoice, etc., etc. But we would lose some information from the payment level, like dates, etc., which cannot be aggregated. You know, you can't aggregate the dates. Maybe we would have the date of last payment or date of first payment. We could not have all the possible payment dates in the purchase invoice level. So we choose the grain, that's the purchase invoice grain, and then we aggregate whatever we can from the other fact. Again, a decision and design made on the conceptual level. The other way around, of course, we would kind of denormalize or allocate values. If we choose that the grain is on this level, this is the fact entity, then we just squish the purchase invoice in there. And what we can do is basically get like the invoice number and date here. But for example, we could not get the total invoiced amount into the payment fact. And this is a mistake many people tend to make, because if we have a purchase invoice for 1,000 euros here and two payments of 500 euros each, if we put the total purchase invoice amount here in both rows, that would mean that, you know, there are two rows, the sum of which is now 2,000 euros. So it's not a summable thing. And often this sort of thing doesn't even make much sense. Occasionally, some kind of allocation based on values like weight or amount of something is something that you can do mathematically in order to maintain the kind of summability, so to speak. But in any case, this is what you can do to combine these. And here I have examples of fact tables created from such a situation. So here we have a fact purchase invoice, which is at the level of individual purchase invoices. We have linked it with the entities purchase invoice and the payment, because we have calculated the sum of all possible payments so far made, number of payments, and the last payment date. So these are kind of things that we aggregated from the payment to the invoice. And the other way around, if we have the payment grain here, we have denormalized invoice number and date and due date here from the invoice level, but we didn't get the amount invoiced total amount here because that would not be summable. That would not make sense. So a couple of possibilities for a fact. Decisions made on the conceptual level, looking at it, how do we squish these entities together? What is the grain? We decide on something and then we get to the dimensions. And again, we need to start pointing fingers at the conceptual model. So what are the dimension candidates given that we have chosen a specific fact? And basically here, what we can do is if we have chosen the fact here to be the invoice, we can start walking through these relationship lines, and every entity which has one on the other end there is a candidate for a fact, because for each invoice we can always find a single purchase order, for which we always find a single cost center, for which we always find a business unit, etc. But we cannot use the bank directly as a, or we should not use the bank directly as a dimension for the invoice, because it is fairly possible that payments for that invoice are made in different bank accounts, which are actually in different banks. So you would get multiple banks per invoice. And we choose our dimensions again by pointing at this graph. So here's the bunch of candidates here. If we choose the fact to be the payment, we can see that there are many more options here. The interesting thing, of course, here is that this means that we could also have the purchase invoice itself as a dimension, which might not make sense in a business sense because it's kind of a transaction. But nevertheless, it's kind of logically possible. And also a thing to note is that the GL account here is not logically possible for either of those facts because it always kind of has this many relationship towards it. Again, you know, with all kinds of allocations and aggregations and whatnot, you could make anything work, but this is kind of the logical thinking process that you can do while you're looking at the conceptual model here. And then you make some decisions. Okay, I want to pick that and that. And you start figuring out, how do I get to the star schema from this? Because this kind of points at a snowflake schema, right? We have dimensions behind dimensions. And at this point of the example, we don't want to do that. So we could denormalize the dimension entities. Again, we can squish them together. So for the bank, for example, we could denormalize the bank dimension into the vendor bank account dimension, saying that the dimension grain is on the account level, but we will just denormalize all the kind of bank related attributes into it, which is, of course, something that always happens, especially with, I've seen this very, very often, and everyone has seen that with product and product categories, you're denormalizing the product dimension, you have all the categories and you know, product types and models and whatnot, all denormalized into the product dimension because that's easier to use. So that's just fine. Because there's a one-to-many relationship here, we can squish them together and denormalize stuff here. That's good. And we end up with something like this. So we have the payment fact here. We have the vendor bank account dimension, and the dimension grain now stays at the bank account level, but we have denormalized bank related information here. We have bank name, we have the risk category for the bank and whatever. We have linked this dimension now in LE very neatly into both of those entities, the vendor bank account and the bank, so that we remember that this dimension table actually contains information about two different concepts. And a kind of risk here is that we end up with something that is not very easy to interpret, and that is an example of that can be found here. If we use an attribute called valid from date in this dimension, it is not immediately obvious, you know, is it the validity date of the bank account or the bank? So naming conventions in this kind of situation are super important. And this is again something that I see some teams kind of falling into this trap of not caring enough about their attribute naming when they are doing this denormalization stuff with their dimensions. It becomes difficult to know what this actually pertains to. But in any case, the result is a neat dimension table with information about two entities which we chose from the conceptual model, and then we made the decision that, okay, we'll squish these together to create a nice dimension. And if we look at the conceptual model as a whole, and we start thinking, okay, well, we could squish these together. How about we squish everything together to make this simple? It is perfectly possible to do so. So if we take this to the kind of logical extreme, we could squish everything together so that we end up with 2 dimensions only. If we want to create a star schema by denormalizing everything like this, we will end up in this situation with 2-dimension tables, one on the grain of the bank account and one on the grain of the invoice. And of course, given that our fact is chosen to be the payment. So theoretically, this is possible. If it's a good idea or not taking any opinions on that. But the interesting thing that we can see from this diagram, if we were to do something like this, is actually now, if you consider the fact that we traversed via the relationships to find the dimension candidates, we will actually see here that we have now, interestingly, different routes that we can take to a dimension from the fact that we have. So consider now here, for example, and pardon my terrible drawing, that we are interested in the country dimension here. So how does the country relate to the payment fact that we had here? We can see that it is possible to get to the country 3 different ways. Yes, actually 3. I think this used to say 2, but there are actually 3 ways. So we could say that, okay, well, the payment is paid to a bank account, which is in a bank, which is located in a country. So the country of the bank in which the account is for a specific dimension. But we can also have another route saying that, okay, well, for the bank account, we have the vendor that owns the bank account whose home country is something. And these 2 countries are not necessarily the same. And there's yet a third option, that the invoice for which this is a payment has to do with a purchase order ordered from a vendor who has a home country. And this vendor doesn't have to be theoretically the same vendor that owns the bank account. This could be a contractor situation or something like that. So because there are 3 routes, again, just by looking at the conceptual model, there are 3 routes between the fact and the interesting dimension. It means that there are 3 different ways that these can be actually related. So now if we do this kind of extreme denormalization, end up with only 2 dimensions, one with the vendor bank account grain here and one with the purchase invoice grain. We'll see that I have linked them to all of those different entities that we have kind of squished into these dimensions, but we can also see that we have the vendor attributes here now, just as an example, displayed in both of these dimensions, but with different meanings. So we have the vendor who owns the bank account versus the vendor from whom we actually order things. And this is again kind of a risk that is taken if you don't consider this kind of closely enough. If you don't look at the conceptual model and realize that there are these different paths, you might confuse these and figure out that, well, there's only one vendor for the payment, but actually there are several with different meanings. So obviously, if we wanted to get rid of the star schema completely, the next step here would be that we will just denormalize everything into the payment factor. We end up with a flat table, which the data scientist community would love, and also some Excel users, but let's not consider that too much. The idea is still the same. So we're kind of squishing things down, and because there are many different paths to the original things in the original model, it means that there are different meanings for the same kind of field, which might be the vendor ID or the country ID or something like that. But what if we don't want to denormalize? So what do we do then? How do we get rid of the kind of snowflake situation? Because even though it is a valid model, of course, in some tools like Power BI, for example, it works quite a lot better if you kind of try to avoid that as much as possible. At least in my experience, it's far easier to work with that. And of course, avoiding joins is something that you probably should do if you have a lower level of SQL maturity, let's put it that way. So if you want to avoid that, I call this maneuver the skip. So if we have a path from the fact to a dimension here, and it's well defined, one bank account per payment, one bank per bank account, we can just easily skip this intermediate entity and link in our dimensional model, directly link the bank dimension into the fact. No problem at all. This is one-to-many relationship, and we can, in the whatever ETL, ELT code we have that generates our dimensional model from whatever, we can determine the direct foreign key from a payment to a bank because we know the bank account in the between. But we can build this in such a way that the end user of our star schema doesn't have to bother with it. So if we're not interested, for example, in the bank account information at all, we can just link the bank directly into the payment and be done with it. And we end up with something like this. We have two different dimensions in this picture. We have the payment fact here. We have the vendor bank account dimension. We have the bank dimension. These are separate things. We know that in the conceptual model in the real world, these two are linked, but we don't have to consider it if it's not important for the reasons of our analytical use case, whatever that is. So there's an extra foreign key here pointing the payment directly to the bank, which can be easily determined and created. It doesn't have to exist directly in the source data. It's just a simple query to actually get that. So what is the result of using these tricks, squishing down or up those facts and dimensions and looking at the model, making those decisions there? We end up with something like this, and this is, as it says in the title, this is a possible example of a perfect star schema. The title of this show here was creating this perfect star schema, but the trick actually is to have different possibilities of perfect star schemas, which are all perfect in their own way. So if we look at this example, we have here a payment fact where we have denormalized some of the purchase invoice information into it. So the fact candidates have been kind of squished together. We have linked that to both the payment and the purchase invoice entities. We have here country dimension, which is linked to the payment directly with two different links. So there are two different foreign keys, one being for the vendor's home country, one being for the bank's location. So understanding the two different paths leads into two different foreign keys and therefore two different links between these things there. We have skipped the vendor bank account dimension entirely. We were not interested in it now. We linked the payment fact directly into the bank. So we have the bank related information here. And we have denormalized the business unit information, which was, if you remember, behind the cost center there into the cost center dimension and used that directly as a dimension of the payment here. And this works, and that's fine enough. I don't know what the actual use case here is, but whatever the needs are, this is kind of logically all right. And this is something that works. So we have achieved something that is ensured to match with the business reality. So we're not kind of taking shortcuts which would endanger the structure of the real model, the reality in the conceptual model. We are just manipulating the structure in specific ways that still ensure that it matches with reality. We can ensure that the quality of the star schema model should be pretty good. All the grains in all those different facts and dimensions should be correct. We understand what they are, what a single row is in every single table. The key structures of these facts and dimensions we can easily build. They're simple joins. I considered that, should I add some rows of SQL here to explain how simple these joins are, but you can imagine them being really simple. I don't want to add any rows of code anywhere if I don't have to. So we can build these key structures very simply. It's just very, very quick joins, no problem at all. And we are doing it so that the data user doesn't have to do it. We have all the data where we want it to be. we have all the data we need. We have just the data we need. We skipped some dimensions and so on. And because we can always go back to the conceptual model, which just describes the realities of the whatever use case we have or whatever scope area we have, we can always go back to the conceptual model and communicate with the business, with the development team on that level. We don't have to go to the level of the kind of logical level of the star schema with all the attributes and foreign keys and whatnot. The business people most likely don't know what a foreign key is. So we can communicate via the conceptual model and always kind of derive the model back from that. So in effect, what did we get was not just, one perfect star schema. Francesco's star schema is the perfect star schema. What we have here are options based on the view that we got from the conceptual model. And we got some ideas on how to think about the conceptual model, how to go about designing this in order to create these kind of good quality matching data models on the dimensional form, which we know are good. And the question that remains actually is what these decisions have to be so that we match with the actual business analysis need. So from, let me take the conceptual model back. From this, using these kind of tricks and rules of thumbs and practical things, which again, nothing new here, but just ways of processing this model. Using these tricks, we can produce all kinds of dimensional models. We just have to figure out what the actual business question was and what sort of a model would correspond to that the best. And then we just use all of these methods to, squish and turn this into something that matches very well. And that's basically the whole point here. So getting options for perfect star schemas with some simple rules of thumb, that concludes my actual talk here.